History of Vector Analysis, Episode 12, Tait's Elementary Treatise. You are here. Hey, it's old Doc Oler. Welcome back. In the previous episode, we met Peter Guthrie Tait, a brilliant 19th century mathematician who collaborated with three even more brilliant 19th century guys: William Rowan Hamilton, William Thomson, aka Lord Kelvin, and James Clerk Maxwell. Tait was at the center of what appeared at the time to be a minor struggle between the question of whether the attributes of quaternions outweighed their weirdnesses. One of Tait's roles was to demonstrate how quaternions could be of practical utility to physics. In 1867, 2 years after Hamilton's death, Tait published his own book on the subject, entitled An Elementary Treatise on Quaternions. Here it is. In my view, this book may be considered to be the definitive text on the quaternion approach, not Hamilton's unreadable tome, and not those that came later because they were all modified by our current model of vector analysis. It was this book that Tait offered to Maxwell, and which in turn influenced Maxwell's legendary Treatise on Electricity and Magnetism, published in 1873. I went back and forth on whether to make an episode on the philosophy and structure of Tait's book. On the one hand, it is not strictly required for our story, and also these techniques are not used today, and the book is written using mathematical structures that are unique to quaternions and, as I discovered, that have a significant learning curve. On the other hand, the book exerted a powerful influence on the development of multiple areas of today's mathematical physics. So in the end, I decided that the pros outweighed the cons, so here it is. You can thank me later. For perspective, I reiterate that William Thomson, Lord Kelvin, referred to quaternions as, quote, an unmixed evil to those who have touched them in any way. Well, I've touched their essence now, at least slightly, so this is a bit of what I saw when I was in there. If you fear for your soul, or if you dislike the idea of viewing a 20-minute video that isn't critical to the understanding of the series, feel free to skip to the next episode. Here is my copy of Tait's treatise. It is a scanned reproduction of an original copy, the first edition, not the more influential second, according to the title plate, and the quality of the printing is downright poor at times. But I have read it. Well, I've read a lot of it, a slow process because it involves not just unique mathematical structures, but also because it is very dense. If the reader misses something the first time, they will quickly get bogged down, and I confess that I spent a lot of time bogged down. But buy it and read it I did, because that's what old Doc Oler does. He spends his days reading obscure math books from the 1860s. Now, you kids get off my lawn. Before we get into it, I want to draw on my maze metaphor. The line you see drawn here is intended to represent the actual twists and turns taken by Tait, Maxwell, and others to express the new 19th century discoveries in electricity and magnetism in the form of quantified mathematical models. This is a wide swath of territory down here that you don't normally explore in college or graduate level courses. I don't expect you to learn how to manipulate the stuff. I'm presenting it to you so that you can compare and contrast it with the stuff that you do have to manipulate, that is, modern vectors. And also, just to show you an example of some math that didn't make it into the textbooks. Here there be dragons. Okay, Tait's elementary treatise. The first thing I'll say about it is what's not in this book. There is no Hamiltonian metaphysics. It is focused strictly on the math, and it is tightly structured. The book is composed of two parts. The first 5 chapters, or about 130 pages, is Tait's derivation of the mathematics of quaternions. The second, slightly longer part, at about 190 pages, is examples and applications. Each chapter contains homework problems at the end. This was intended to be a functional textbook. Tait begins straightforwardly. He introduces the square root of -1 and then introduces imaginary and complex numbers. But then, an abrupt pivot. He writes, but for the purposes of elementary exposition, it is best to begin by assimilating the ordinary Cartesian methods of geometry of 3 dimensions. That is, he is going to start off using only those 0 real quaternions that we discussed earlier, where the coefficient w is set equal to 0 and the quaternion itself is composed of just 3 parts. He will call these vectors, but remember that they are not our vectors. He represents them in his text with lowercase Greek letters, alpha, beta, and so on. Then he notes that Points in 3D Cartesian space require 3 parameters to define them, which just so happens to be the number of non-zero parameters in his so-called vectors. So he can use one to represent the other. Here, the vector alpha equals ix plus jy plus kz, where x, y, and z refer to numbers along 3 axes that don't have to be orthogonal, but usually are. Tait uses italic Roman lowercase letters to represent scalars, and will later use non-italic Roman lowercase letters for general quaternions. It gets confusing. Now, and this is important for both Tait's story and ours, he does not explicitly define I, j, and k, other to infer that they are associated with direction. This allows the reader to assume, falsely assume, that I, j, and k are real unit vectors along the x, y, and z axes. Nothing up my sleeve. He then proceeds to define vector addition with the identity, inverse, commutative, and associative properties. He also defines scalar multiplication. Just one number, a scalar, is required to transform one of his 3D vectors into another that is parallel to the first. Finally, he introduces some of the concepts needed for vector differentiation, and then concludes with a number of examples in which he shows that vector operations reproduce many of the proofs in Euclid's geometry and are thus consistent with it. Tait's chapter 2 is entitled Products and Quotients of Vectors. Adding and subtracting quaternions or vectors is not enough, as Hamilton noted many years earlier. The system should be able to support and interpret multiplication and division as well, along with exponentiation and roots. Tait starts chapter 2 of his treatise with a jaw-dropper. Instead of defining quaternions as q equals w plus ix plus jy plus kz, with I, j, and k all being equal to the square root of -1, as Hamilton and we did earlier, he begins with an observation. He noted in chapter 1 that the number of parameters it takes to transform one vector into another that is parallel to it is just 1, literally a scaling factor. What about the more general case? How many parameters does it take to transform one of his 3D vectors into another when they are not parallel? He shows that the required number is 4. 1 for scaling, as before, and then 3 to do the rotation. This includes 2 angle parameters to specify the plane that the first vector must be shifted into, and then 1 more for the amount of rotation within that plane. 4 numbers to convert one of his 3D vectors into another. This conversion process can be done either by multiplication or, get this, by division. Okay? He defines a quaternion as the quotient of one 3D vector divided by another. Okay. I was quietly stunned when I first saw this. In modern vector analysis, vector division is not defined, something that I will prove in the episodes ahead. Tait replies, no, division of one vector by another is perfectly well defined. It simply requires 4 dimensions. But that's not all. Tait drew on Hamilton's geometric argument regarding a left-handed 3D coordinate system, left-handed because multiplication in the established 2D complex plane by a positive parameter results in a counterclockwise rotation, okay, with unit vectors of capital I, j, and k along those axes. I showed these figures in an earlier episode. Now, consider the lowercase I to be the 90-degree rotation operator around the axis defined by the capital I unit vector. Counterclockwise rotation about this axis would transform the unit vector j into k. So I, j equals k, right? Just like complex numbers. Now, what is the inverse of this process? How do you rotate k into j? Well, it seems straightforward. You multiply k by negative I. Positive to go counterclockwise, negative to go clockwise. Let's bring some algebra into this geometry. Let us substitute j equals minus ik from the second equation into the first equation. We get this. Now we divide through by the unit vector k. Vector division is not allowed in our vector analysis, but it is in Hamilton's and Tait's. So we get this, which can be arranged as this. I find this to be clever and weird at the same time. Tait hasn't postulated that I, j, k are imaginary the way we did earlier when we were trying to follow Hamilton's elaboration on the complex plane. No. He has derived that ijk must be imaginary based on the assumed rotation properties of Tait's vectors, which in turn came out of his definition of a quaternion as one vector divided by another. For Tait, 4D isn't an unfortunate consequence of needing I times j to equal k rather than 0 or plus or minus 1 or something like it was for Hamilton. Rather, 4D is the essence of quaternions, the central unifying theme. 4D comes first, all else follows. Also in this chapter, Tait proves that quaternions are not commutative under either multiplication or division, but that they are associative under multiplication and division. Rather remarkably, at least to me, he proved these two properties geometrically rather than algebraically, as I did earlier. To Tait, quaternions are geometrical first and algebraic a distant second. One other thing that Tait does in this chapter, following Hamilton this time, is to group the four parameters you get when you divide one vector by another into two operators. The first is the single parameter used for scaling, which he refers to as t. T stands for tensor, but it is not our kind of tensor. In fact, Tait's tensor is the magnitude of the quaternion, which is technically what we would call a scalar today. The three parts that are associated with the rotation of one vector into another is called the versor. But he expresses this term using the letter u, presumably because the letter v was already taken. Tait notes that scaling and rotating are multiplicative operations, not additive, but that the order doesn't matter so that t and u commute. Okay, he also defines k alpha, which is what we would call the complex conjugate, or in this case the quaternion conjugate of the quaternion alpha. K alpha is also a 4D quaternion with the property that alpha times k alpha yields a scalar product, the square of alpha, which is also equal to the square of t alpha. Okay, as I said, here there be dragons. Chapter 3 introduces several new quaternion operations to the reader. Two of these we have seen before, S alpha and V alpha, the scalar and the vector components of the expression alpha equals W plus IX plus JY plus KZ, which we saw in several earlier episodes. What Tait immediately points out is that we now have two ways to break up a quaternion into two parts, S and V, which are added, and T and U, which are multiplied. What follows is the derivation of a large number of identities relating these four operations along with K, the conjugating operation, to each other, and using these to prove many of the results from Euclidean geometry. I confess that I spent a couple of days trying to work my way through this chapter, but I found it a lot like trying to read Homer in the original Greek. Okay, I'm sure it's beautiful, but at this stage of my life, I just don't think I'm willing to commit that much effort to learning what is essentially a new language. But having said that, there are some really cool things that appear in Chapter 3. First, Tait considers the product of two quaternions. He begins with the S and V operators acting on the product of alpha and beta, and then relates these to T and U operators acting on alpha and beta individually, and comes up with this in the box. If you look closely, you may see something familiar. These expressions are close to what we recognize as the dot product and the cross product of two modern 3D vectors. I say close because they aren't quite the same. Vectors A and B lie along real axes, while the quaternions alpha and beta lie along imaginary axes, and Tait's theta is defined somewhere in 4 space. Okay, but you can see the significance. Later, Tait introduces the evaluation technique for multiplication of two zero real quaternions in terms of taking the determinant of a 3x3 matrix, not a 4x4, but a 3x3. He also demonstrates the ability to execute a pure rotation without scaling via multiplication of the target object, something I dedicated an entire episode to earlier in this series. Chapter 4, Differentiation of Quaternions, is a mere 7 pages, but it still contains a lot of highly structured material. Tait goes back to the original Newtonian definition of fluxions to introduce the differentials rather than the derivatives of these multidimensional mathematical objects. He discusses the change of one quaternion with respect to another, but he does not introduce the del operator in this section. Reading through chapter 5 gave me flashbacks to my first year of grad school of reading Jackson's infamous textbook on E&M. It wasn't simply that I had trouble following the math. It's that, once again, I didn't seem to understand where the math was trying to go or what it meant when I got there. Humbling. Tait states in the introduction that chapters 1 through 5, quote, have been drawn up so as to give the student a short and simple summary of the chief fundamental formulae of the quaternion calculus itself, unquote. Chapters 6 to 11, which actually comprise the majority of the book, are intended as mere applications and examples of the quaternion math to geometry and to physical problems. These chapters are unique to Tait. This was the stuff that Hamilton didn't bother with. I've listed the chapter titles here, but I'm not going to go into much more detail, with the exception of the del operator. Tait first mentions del not in chapters 1 through 5, but in chapter 9, almost as an afterthought. I suspect that this is because Tait, like Hamilton, basically considered the 3D operator del to be a mere application of the 4D quaternion differentiational process. But having said that, he takes the math pretty far, including presenting a version of the concept of 3D divergence. Don't forget that Tait's IJKs are not the same as our IJKs. The title of chapter 10, Kinematics, implies a desire to have quaternions appeal to the scientific community. It again includes the 3D del operator. It's murky, but the concepts that would become divergence and curl are in here. Tait goes so far as to write a form of Gauss's law in quaternion form, where R in this expression is a density. Chapter 11, flat out entitled Physical Applications, to further attract interest outside of the pure mathematical community, again uses the del operator to derive a number of quasi-familiar identities of use to physicists and engineers. It was Hamilton who first identified the del operator, but it was Tait who developed it. At one point, Tait applies the del operator to a special 4D quaternion alpha that is itself the product of two 3D zero real quaternions, and shows that it can be expressed in a way that is analogous to what we here would call S dot alpha plus V dot alpha multiplication components that we defined earlier. As before, Tait shows that the scalar part of del alpha is this, and that the vector part of del alpha is this, which resembles, in many ways, the divergence and the curl of a modern vector field. Tait does all of this before he writes to Maxwell. It is important to note that, at least in the first edition of Tait's elementary treatise, which is the one that I have, he does not include a quaternion derivation or formulation of the pre-existing Gauss's theorem, Green's theorem, or Stokes' theorem. This is important for our story, for it was these derivations that Maxwell will himself use at the very beginning of his classic 1873 Treatise on Electricity and Magnetism. There may have been some back and forth between Maxwell and Tait on this. Tait did publish papers on these theorems in 1870 and 1872. To summarize, Tait's book on quaternions is a remarkable piece of mathematics. It is very well organized. The struggles I had in translating it into math that I was more familiar with were twofold. First, quaternions really are a different language than vectors, and at this stage I'm just not willing or able to put in the effort required to try to become fluent in that language. Okay. The second source of objection was the fundamental 4D nature of these mathematical objects. Note that these four dimensions are not the same as the four dimensions of special relativity and general relativity. Einstein stated that his starting point for special relativity was Maxwell's equations, but we know that it was the 3D non-quaternion version that he used. What would Einstein have done with the quaternion version of Maxwell's equations, which were already 4D before you considered time? Perhaps relativistic quaternions would contain 5 dimensions or 8? I will wimp out at this point and leave such questions as an exercise for the reader. Okay, final question. Was William Thomson right when he wrote that quaternions, quote, have been an unmixed evil to all who have touched them in any way? Right, the comment seemed almost silly to me when I first read it. Hyperbole, no doubt. But the more I studied Tait's book, the more I came to believe that, yeah, well, maybe Kelvin had a point. Tait's quaternions are not only fundamentally 4D, they are also fundamentally geometric rather than algebraic. It's funny, but I have no conceptual problems manipulating infinite dimensional Hilbert space, but Tait's apparent view that a 3D vector is not real, but rather a special case of a true 4D object gives me a headache. Okay, maybe it's just that I'm old. All right, that's it for this episode. Next time we'll change directions with a bit and we'll discuss a young James Clerk Maxwell's fascination with 19th century field theory, then in its infancy. See you then.